Today I will tell you a story how we are solving data quality at Spotify. So who am I? I am Mārtiņš Kalvāns. I have worked at Spotify for almost 4 years. When I started working at Spotify, I had no big data experience, and ever since I have worked only with big data infrastructure. So I am providing tools for our data engineers so they can easier and better process their data. So today on the agenda is 4 points. Like, we will start with a little bit of context, data and Spotify, how we use it. Then we will have a story about some incidents where most of the learnings about data quality comes from. And then we will go into how we learned and what actions we took to improve the situation. And as in conclusion, we will have some hints how we are trying to drive adoption of those tools. So let's start with what is Spotify. Spotify is one of the biggest music streaming companies in the world. We have more than 100 million active users. We provide more than 30 million songs in our catalog, and the users are making 2 billion playlists. And we have to provide all of that in 60 different countries. So how do we get those numbers? By building an awesome product, or we tend to think that way. So we use data to drive our A/B testing decisions, so analysts can slice and dice data and do the analysis there. There are also purely data-driven products in our application, like Discovery Weekly, Daily Mix, and there are other products that are improved based upon the data. Even the search or browse is using the data pipelines to improve their products and their offering. As well as that, we have an external liabilities. We need to report to our labels every month about the usage. We provide billboards with data, and there are even some third-party partners that we need to provide with data every day. So every product, every report is generated by some team. How does it happen? So normally, when we talk about big data, there is a team responsible for so-called core data sets. They are responsible for making a playlist dump available on HDFS. There is a dedicated team, all dedicated to event delivery. So all the events that happen on your mobile device when you play the music could get to the Hadoop server for other teams to consume and slice and dice data so they can improve their product or based on the data, make it better. And here, I think we need to step back a little bit and talk about our Spotify culture and team setup. Every team is focused on speed and experimentation. That's at the core when we work at Spotify. We want to verify our hypotheses very quickly and either reject them or validate them, so we can either kill the code base that is not useful or make it production ready and publicate it. So to achieve this speed, every team has a great deal of autonomy. They can choose how they build the microservices, as well as they can choose what big data technologies they want to use. And the same goes for the data dependencies. They can choose whatever is available on our big data storages, and historically it has been Hadoop cluster. So they can browse around or discover new data sets that might be beneficial for them. And quite often it happens that team that is, for example, responsible for Discovery Weekly would build a very interesting data set that would describe user taste profile. That data set could be used by other teams to improve their product as well as a side effect. So they would go ahead and publish it. Hey, we built this awesome thing. Everyone can take and use it because we already took an effort in building it. On the other hand, there might be cases where teams independently find some interesting data set on HDFS and start using without notifying the owner. This is a little bit worst case, and it has happened that someone starts using a data set in production that was meant for hacking only, or is only sampled subset of the original one. So that doesn't end well, and incidents might happen. So how does it look graphically, this dependency? This is a nice picture. It shows some of the structures in a small scale between some of the data sets and some of the teams. There is nothing more than an artist. It's more like an art form rather than useful information. To get the fuller picture, we can look at this dependency graph, which looks more like a mess. So imagine there on the left, those are the root data sets, like from event delivery, database dumps, and teams do consume those data to slice and dice, produce new data sets, and other teams can then pick them up again, reuse it for their products. And on the right hand, the core of the useful data for the products would arrive, like your weekly Discovery Weekly playlist. So yeah, this is just also zoomed in picture. So we had this tremendous user base growth, and we are still growing. And also, more and more teams started using data sets. So both factors contributed to our data usage on our Hadoop cluster. The user base is growing, so more data is coming in. More teams are adapting big data technologies. They want to use it to leverage it and to improve their product. That means that the strain on our Hadoop cluster was growing, as well as event delivery pipeline. And that converged in 2015 during the summer that we nowadays call the summer of incidents. At first, it seemed like an unrelated stream of incidents are coming in for no good reason. But soon we realized that the cause is bigger than we anticipated, and we huddled up like 10 brilliant engineers in a war room where they worked long hours trying to figure out what is going on and to deal with the incidents and remediations. What actually happened? Well, Hadoop cluster was barely keeping up with demand of data processing, as well as event delivery, like the Kafka pipeline we had at the time, was also barely catching up on all the events that are coming from all different sources, from the server, services, from application. That means, so in a previous picture, you saw the dependency graph. On the left, you imagine that's the event delivery artifact, the data set there. If it gets delayed, what happens? Every downstream dependency gets delayed too. So if event delivery catches up and makes data sets available suddenly at the same time, all the dependencies will request Hadoop resources and try to catch up themselves, as they are usually scheduled in a recurring manner to try to run it. If it fails, try again later. That meant one thing, that Hadoop couldn't keep up with these requests, with these large amounts of requests at that time. And it would bring down our Hadoop cluster. It was basically DDoSed by all those jobs submitting, like from the edge nodes where we usually schedule our jobs. And that means if Hadoop is down, event delivery system can't deliver their data again, and the data gets delayed. So it's a never-ending cycle in an incident. What those engineers ended up doing is quite unordinary for us to stop this wave of job requests for Hadoop cluster. They firewalled off all the edge nodes from our teams and allowed requests only from Kafka event delivery. So at first we can catch up with core event delivery, and then allow some edge nodes that are more important, like for reporting, to catch up those, and slowly open the gate to the other teams. So the reprocessing of data was happening not immediately, but it was quite a labor and quite a manual work to make it happen. After the summer of incidents, we did, once the Hadoop cluster was brought up, once we stabilized the system, once the capacity plan was implemented in a better shape and we had the resources, or at least we thought that we have the resources to process for the time being more data, we could start analyzing what happened. So there were retrospectives and postmortems after the incidents. And we identified that we are lacking some kind of quality when it comes to data. What is the data pipeline overall? Like you take a data, then you have a program data pipeline that is quite often Hadoop MapReduce job. That, as input, takes one data set or multiple data sets, does some calculation, and stores the output to the target data set. So for the pipeline itself, the default software engineering practices apply. The code usually we write in a crunch or scalding, that is Hadoop abstraction frameworks. Those are the ones that we used at Spotify quite heavily. Nowadays, as we are moving to the Google Cloud, we try to leverage Google analog to Hadoop. That's Google Dataflow. And historically, we have used Luigi Python streaming. So in all of those frameworks, it is quite easy to write a code and express your business logic in a few lines of code as you wish to do it. So we didn't see much of the problem there. Of course, after the code is written, you can enforce it with code test coverage and all previously mentioned frameworks and many others out there do support very nice integrations in either JUnit or specs or whatever you are using to run your unit tests. And some might say, oh yeah, but in test-driven development, tests come first, but I put them second. And after the code is written and tested, you want a very stable continuous integration and deployment. We use GitHub Enterprise, so we make a pull request when we want to modify the code, and then it is very nicely integrated with Jenkins builds servers, and there is a even dedicated team for improving this code build process, and by providing a very simple description how to build your project quite often in one line, you can get this integration for free, and in GitHub pull requests you get immediate feedback. Did your tests fail to run? Or maybe if you enable check style or find bugs, also feedback about that you can get easily back. The only thing in this software engineering practices that I would say changed since 2015 was that instead of building jar files that we deploy, nowadays we do deploy Docker images. So our artifact after building is a Docker that we ship for execution and scheduling. So I will not touch more about this one. What we identified from the incidents was that the issue was somewhere else. How we noticed that incident is happening. In 2015, quite often it was some kind of reporting team that was expecting by the end of the month or end of the week to find a report file that they need to send to our partners. And when they don't find a file there, they start raising hands and raising an issues, what's going on. And then it is already way too late to quickly fix it. So many engineering hours need to be dedicated to catch up, as I told previously. That means that we could probably improve this process or the state of our infrastructure if we had a better monitoring for data or lateness. So let's talk about how the data usually looks like. Like normally in batch processing, you have some data set word count, and it would be bucketed into partitions based on date. And it could be hourly or daily buckets, or maybe weekly or monthly. So then you can ask a question, if today is 26th of April, where is the data for 25th? We have a 24 as last one, but there is no 25th. So of course you don't expect in data for it to arrive at the midnight after the 25th, but after some while, the data should show up if it is correctly scheduled. So based on this information, we set out to figure out what are the minimum set of information. If we want to build a monitoring system, what is the information that we need to know to build it? So we came up with some metadata that we require. So first of all is, of course, dataset name, and then the partitioning. So is it hourly or daily or weekly partitioned? And then we would need also to know where the data is stored. Is it stored on Google storage? Is it stored on BigQuery? Or is it stored on HDFS? Like we had to support all our different storages as we do store data in many of those. And the URI would include a pattern for that we would fill in with the date, with expected date for particular hour. And then, as we can't predict when the data is arriving, and different pipelines might have a different processing length, or if they are at the end of the processing chain, they are all the upstream dependencies are contributing to it. So the users would need to define when is the data expected to arrive. And how would we alert if the rule is broken? So we choose to integrate with external PagerDuty system. Why? Because that's nothing new to the Spotify. We have used PagerDuty in many other monitoring systems. Most popular is service uptime monitoring. So that would be nothing new for developers that are working in other area, not data. Also, we would require this information to be present together with the code in a same Git repository in a simple YAML file. Again, that was not our invention, because YAML files as system descriptors were used for services and other components at Spotify. So we had already service that would take care of aggregating them and displaying the ownership and description about our components like services and now about data. So in addition to these required properties, we would get for free another a set of properties that is description, ownership, the life cycle of the pipeline for free, which is a nice benefit. So given this information, we set off to implement the actual monitoring system that we call the datamon. So given the information from YAML files that we would refresh every now and then in a datamon, it's a bunch of microservices that is represented with one cog here, but in actuality, we implemented as many smaller microservices. It would gather the information about datasets that we need to monitor. And then it would query all the different URIs or the storages to figure out which partitions are missing during the time period during the last week. And then that information could be fed in a dashboarding system for nice GUI user interface, or to trigger an alert in PagerDuty. So the GUI would look something like this. It actually looks exactly like this. So every row represents one data set, and most of them are partitioned in hourly buckets. Two of them are partitioned in daily, so you can see long stripes there. And most of it looks good, but those who are not colorblind like me can see the red spot there. That means that one particular data set is is breaking the lateness rule. It is behind in delivery. And it means that a PagerDuty alert was already generated and sent to the owner of the dataset, so they can start fixing and dig into the problems what they have. So when we implemented this system, we started by adapting with our core event delivery team. The feedback we got was very positive. Like they said that they had prevented incidents at large scale once they could get easy alerts in time. And the benefits that Datamon provided to other users was also quite noticeable. As of this week, we had like 4,000 data sets registered in Datamon. So we could take care. Now we consider the data lateness monitoring as a solved problem with smaller incremental steps that we can always improve upon. So let's move to the next challenge. Once we have lateness in place, we can look what is the missing part in data quality as a next step. And it turns out that checking data sanity is just as important. Like, you remember I talked about if something is delayed, it would result in spikes in resource demands that are hard to cope with. Well, sometimes the data would appear to be okay. So the data would arrive to the HDFS. But it would arrive in a bad state. Like Kafka pipeline, due to our developer bug or some other system error, would produce either partial data or by retrying something would produce duplicates in a data and mark it as complete. So all the downstream dependencies would start consuming wrong data, and without noticing it, would produce results based on data. And whereas if the data is missing, it's quite easy to spot if you are on a Hadoop command line, just list the directory and you see, oh, something is missing. If the directory is there, but it contains wrong data, that's not so easy to spot. So whenever such cases are caught, all the downstream dependencies should be nuked and deleted, and again, the reprocessing should start again. That was unfortunately these incidents happen way less than just delays in data. But still, we identified it as a problem where we can improve. So what can we do to check data correctness? Some data sets can come in big sizes, like petabytes, maybe not, terabytes easily. So in Hadoop, when you do the data processing, you can use Hadoop counters that is provided by Hadoop API. In this simple code snippet, you can see how in artificial example, we assume that there is an input logs file that we want to parse, and we assume that some log lines are invalid and unparsable. So this particular is scalding code, but don't pay attention to API. The idea is the same everywhere. You can write a code and validate. If the line is correct, you can increase the parsed lines as valid, the counter, or if the line is invalid and unparsable, you can increment a counter responsible for invalid lines. So this looks pretty simple, and after the pipeline has run, you can look at the values and define some rules. Like, I expect that not less than 1% of all lines are invalid, and have that as a rule. If it's more than 1%, then fail the pipeline and stop the data processing. The example is simple, and it works in most of the data processing frameworks. Unfortunately, that does not encapsulate what data engineers really wanted. Let's take a look at some counter over the timeline, over the partition time. You can see that the counter is monotonically increasing slowly, whereas there are few spikes which are clearly anomalies, and we would like to catch them and process them and decide what to do with the data. In all of previously mentioned data processing frameworks, crunch, scalding, that we use at Spotify, we don't have an access to previous partitions. There is no concept of partition there as we use them. So an additional requirement for such anomaly detection would be that we are not only using Hadoop. Nowadays, we are moving more and more to Google Dataflow, which has a different API to gathering counters. And with these requirements that we want to do anomaly detection over time and support different or be framework agnostic, we set off to build a system that would solve this issue. So in this example, how the code flow would look like. So you have a data flows job or any other job that would produce some numbers, some counters that describe your data processing. As previously, it could be processed lines or rate of error. And then at the end of the pipeline, you would publish the counters to our counter service that we built. That would have, in this case, persistent storage with all the history available. And as a separate step, you can define a rule engine or verification code that would grab the current counter value, ask for the history, and then do smart stuff or simple stuff, depending on what do you want to verify. For example, quite often you want to verify that your data is growing within some bounds, like 10%. And whenever it is growing or dropping by more than 10%, you can again fail the pipeline, send an alert, and someone will come and look at it. But what happens, how do you choose these 10%? Like the tools we gave user, the tool is pretty simple. You just take an API, you can publish something, you can get back. But whenever you're, like, let's assume you have a hammer. That's also a simple tool. And you want to hang a picture on the wall. So it is simple. You just nail a nail and you hang a picture. But how do you decide where it will be nice looking, or how do you hang it so it's not tilted? So the same question came in this context. How do you choose this boundary? What is the good error rate? If you choose it too small, you will get over-alerted. Incident fatigue, you start ignoring the incidents, and the system is useless. If you choose it too wide, then again, it never catches an actual error, and the system is, again, pointless. So what we recommended our users to do is to define two boundaries. And this pattern has proven working previously in other squad. So you would define two boundaries for warning and for error. For example, the rate of change, if it increases more than 10%, you would generate a warning result. You would send an alert, but the data would get published. You wouldn't fail the pipeline. And if the error rate is more than 30%, you would still send an alert to the data owner, but you would also stop the pipeline. You would fail with an error, and the data would not get published. And if the error rate is within the expected bounds, you would just say data is okay, and all the downstream jobs can consume it. As I said, we learned this from one particular team in Boston that has used this pattern previously. And you would think quite often in user interfaces that more knobs or more parameters to manipulate the system is more complex. In this case, it proved other way around, because when you can define very strict for error for warning and very quite loose for the error, you can encapsulate this gray zone where you don't know where exactly the error rate should be. So once we had these tools available, the question became, how do we drive the incentive for our data engineers to use them? Because one thing is knowing, another thing is doing. When I started coding, I didn't write any unit tests. When I started working in my previous companies, they also didn't write unit tests. And when I moved to a company that does unit testing, it was a groundbreaking something. I needed to change my behavior. So in this case, we have tools to check data. How do we tell our data engineers to start using them? Even if we make API as simple as possible, it is still a change that they need to do in their behavior to start actually doing it. So the independent team of people formed a test certified for data group. What they would do is they would drive this incentive. They would define the requirements for data pipelines so the data pipelines could get certified. And at first level would require some basic unit testing, saying continuous integration and deployment setup, whereas level 2 would require them to have lateness monitoring, defined service level agreements, some metadata description, where in the life cycle the data pipeline is it production or in experimentation. And level 3 would be a requirement where team needs to know very strictly where they are in equality. They should be very confident that their data they deliver are in timely manner, and that the validity of the data is there. And of course, the reward for each level would come in some form of candy, and in this case, there is a swag for those teams that go through the certification. Also, they could annotate their data pipelines with a certification level. So other teams notice that, oh, this neighbor team has gone through the data pipeline certification, and they have this badge for their data pipeline, so they get jealous and they also apply for certification. And it works like right now. There are approximately 10 teams that are going through the certification process for different levels. At the end, what we want is to promote overall everywhere at the company that to think about the data quality as much as possible. So the takeaway for you, I think, is asking yourself, what is the confidence for you in your data pipelines? Are there any areas that you might be lacking these or maybe others, and what can you do to improve those? I hope you can take some learnings with you. Thank you.